Hello, I'm your host, Grayson Brulte. Welcome to another episode of SAE Tomorrow Today, a show about emerging technology leaders and innovators to make it all happen. On today's episode, we're absolutely honored to welcome Ted Bohn, Principal Engineer, Center for Transportation Research, Argonne National Laboratory. On today's episode, we'll discuss why megawatt charging may be the missing link for electrification and the role standards will play in making it all scalable. We hope you enjoy this episode. Ted, the national labs are cool, and that's the kid in me coming out. So welcome to SAE Tomorrow Today. I'm excited for this conversation.
Yeah, thanks for having me. We've got lots of scientists and applied scientists, and that's kind of the area I work in.
We're going to focus on megawatt, high charging. I played golf with my buddy Richie, so got a good download over the weekend about this. Let's kick it off. What is the role that standards play in the megawatt high volt charging industry?
As most people know, the joke standards, we get hundreds of them. And so what people want to have is one standard. When you go above 500 kilowatt, can we just all sit in one space? And so below 500 kilowatt, there are lots of, Chinese standards, Asian standards, German standards, US standards. They are somewhat interoperable with adapters, which is good, but wouldn't it have been great if we could all just take one step back and say, let's just have one. And that's what happened with the MCS, the Megawatt Charging System, and Charan and SAE and IEC working together to say, let's not have the Asian version and the US version, Finamo and Chaoji. Let's just have one. And that's where we're at today. And then, we were talking before about scale up in the mining industry. They want to have multi-megawatt. So they want to go up to 60 megawatt with the same type of things, but more contacts. And so that's the other, it's a big part about all this is say, if we can keep the controls the same and scale the power from hundreds of kilowatts to single megawatts to tens of megawatts, that really becomes globally powerful. And the same with marine and aviation to say the functions are identical. The form factor, especially on the sealing and the environmental part, is the variation. Just to be clear, mining and marine needs something more robust than something you use on the road.
It's fascinating. How do you scale up? You said, let's use mining for example. You said 60 megawatt. That's a lot of energy. Now, and I'm going to go back to the kid in me. I'm afraid of the kablooey situation. How do you scale it up?
Those cases would infer that if you have an autonomous vehicle, you have an autonomous charger, right? So the vehicle that doesn't have a driver is charged by a technician that is a robot. And then the same, these higher powers are, just to be fair, much higher voltage. And so the 1500 volts and the 1250 volts in the MCS standard have something called the defibrillation limit. So if there are stray capacitance charges up one of the wires and you touch one of those wires, there's a limit at how much energy your body will survive once you touch that wire. And that's where the 1250 volts for humans without gloves go. So in mining, you're always wearing gloves. And then above that, you're not going to have a human. You're going to basically have robotic vision. It's going to open the door, plug it in, unplug it. And again, none of this is energized under power. So it's always energized and de-energized when your hand is not on it.
Do you see robots and robotic technology being one of the keys to unlocking megawatt charging at scale?
It's an accessory. So if you have to do and again, an expense to say, if I have a robot per plug, that gets to be a lot. And so there are companies who have a robot on a track where the robot actually drives down and it can see the plug, unhook the plug, put it into the truck, and then it pulls its arm back and goes down to the next row. So much like a valet that can go down a row of vehicles. But again, that track, all that overhead it adds up. So, and again, one robot per plug is important, but if that plug is serving a $20 million vehicle that is running 24/7, like on the autonomous mining trucks, it's justified.
What role does SAE J3271 play in this ecosystem?
So as the chair of that, one of my monikers in the beginning was rolls, flies, or floats. So in the beginning, everyone thinks of J1772 as a connector standard. 3271 is a system standard. It says megawatt charging system. It doesn't say megawatt charging plug. And so this one goes from the point of interconnection, where the electricity leaves the sub transmission, goes through all the power conversion to the connector, through the connector, and to the battery terminals. That's what 3271 covers. In other standards, there's a whole forest of, there's one for the inlet, there's one for the plug, there's one for the communication, there's one for the cybersecurity, and on and on. This is a one-stop shop that has sections in it. So it's almost like Encyclopedia Britannica. It has many volumes inside of one document, and that makes it cohesive, where I don't have to be compatible with other standards. It is the standard itself. And then, of course, they are interoperable and harmonized with other global standards.
Well, I'm going to say this in simple terms. Is it fair to say that 3271 is very broad and can go across multiple use cases, as you said earlier, with
That was the
maritime?
point of 3271, is that it covers the rolls, flies, and floats aspect, not just the connector, but all the different ways it's done. So you talked about the autonomous charging. Another part is aircraft. Aircraft, you have to have an extremely short cable for an extremely long distance with wings. And it's like, well, how do I make the cable not 100 feet long? Because 100 feet at 5,000 amps or 3,000 amps is a lot of copper, right? And so one thing people want to do is have a pit. So the aircraft either lands over the pit or rolls over the pit. You open the door and you pull the connector out and you shove it straight from the ground up to the wing. That's the shortest distance. That has to be written in a standard. In the 61A5123.3, and again, just say the Charin reference document, we specified where in the vehicle the inlet is so that the cord can be as short as possible, because most people drive light duty vehicles, say it can be in the bumper, it can be in the tail, it can be on this side, it can be on that side. And again, especially on buses and trucks, it can be on the not driver's side, and that's a problem, right? So you have to drive the opposite way to get it close enough to get to the plug. So that's where standards come in. They say, we have mandated that the inlet on these vehicles shall always be in this location, and we get away with a 2-meter cord versus a 10-meter cord or a 30-meter cord. So that's a really big part of why the use cases on the standard are important.
I'm curious about this. What makes SAE J3271 different from the IEC and the ISO standards already associated with megawatt charging?
Those are the subsections I talked about. So each one, so 61A5123.3 is just the EDSE side. 5474-3 is just the inlet on the truck, right? The TS 63379 is just the mechanical specifications for the connector. 5118-20 edition 2, is just the protocol. And so, and again, same with the -10 on the automotive Ethernet. And you can just see how you have to buy 20 standards to get it all in there, versus the SAE document has everything in one and it references the other standards. So it just has a different philosophy of clean sheet versus an extension of a previous standard. So that's where that 61A51-23 is DC, -3 is MCS DC. You're like, oh, so this is the wings on a building. It's like this one plus this annex plus this annex plus that annex. That's how they're designed, that they are backward compatible, but they also have a whole bunch of boilerplate and heft. So this one, again, you want to have a very user-friendly one, and then there are variations. Just to kind of you didn't ask, but I'm just going to say there are specific standards for other applications. So for instance, in aircraft, there's the AIR 7357 is just aircraft, because for instance, aircraft charging areas, or whatever you want to call it, the area around it, there's certain color lights mean different things. So if you put blue lights on the side of your charger, someone could be using that as a guideway light, for instance. It would be the wrong color for that application. So you have to have a standard that says you may not use this color lights on your charging equipment because it means something else, for instance. So that's why they are based upon that. So again, the 7357 3271 covers everything. 7357 just covers when it's an aircraft. What does it have to do? And it ignores all the stuff for ships and other things. So you can kind of see how you can have a recipe that is tuned for a specific use case versus the 3271 is all use cases.
So with this clean sheet approach, does that unlock scale?
It, again, because it covers more than just the connector. A lot of people think that when you're holding a connector in your hand, for instance, this one or this one, they just think about the contacts. They say, this is the standard. It's like, no, this is the middle of the standard. Everything that fed, just like milk doesn't come from the fridge, it comes from the cow, right? And it also comes from grass and it comes from the sun. It's like, oh, well, that's kind of what this standard does, is that interconnection power, you have to describe how the power got to the power electronics. And of course, when you have an array of 50 chargers at one facility, how do you manage the facility? So there are IEEE P2030.13 is a functional specification for how you do that. How does that overlap with the others? That's where the interoperability comes in. And again, just to be what I call full disclosure, I'm the chair of those other things. So when you say, do you agree with those other authors? I am those other authors. The way we wrote the other standards were pointed towards this one, and the way these are written are pointed towards the other one. So they were proactive. That the reason we use these words were to make sure they are intended to use with these other things. But anyway, that's supply side dynamics of integrated charging, integrated photovoltaics, and now with solid state transformers. all these things are uh, unknown territory before, but are definitely necessary for scale. And as most people know, the lead time on your interconnection permit can be years. And so there are some people who have short-term things to say, well, I can work off-grid until ... or I can maybe make this an off-grid focus one where the grid is the backup to say if the sun doesn't come out for a couple of days, we can run at 20% capacity if there's no sun.
Then, I mean, you raised the interconnections, one aspect of it. I just think just from a facility, let's just use, if you want to use a trucking facility, electrification for trucks, Class 8. Where's the energy going to come from? What infrastructure has to go in the ground, and what type of backlogs are there? I mean, obviously you got the permitting backlogs, but are there equipment backlogs? What goes into that?
So the norm today is to have things that are fed by 480 volts AC, and then you have a distribution panel, and then you have single or multiple transformers and multiple power converters, and that's where the limit is. Usually have 2.5 megawatt MVA transformers, right? So 5 MVA is kind of what you're going to top out on. And so if you want to go higher, then the facility has to own the transformers and the switchgear and all the other things. So that's where solid state transformers come in. That's where, I'll just name drop, Watt EV has their product now that runs at 1.2 megawatt, and they have clusters for data centers that are running at 24 megawatt. And you're like, well, why would you, what does that mean for data centers? It's like, well, luckily data centers run at 800 volts DC, much like trucks. He said, but 24 megawatt, that's 30,000 amps. And that's the output. So you can kind of see how this stuff takes space, and having solid state transformers instead of conventional low frequency transformers is kind of the future. And that's where the lead time on some low frequency transformers can be many months to years versus the solid state transformers. There are about 20 companies who are getting ready to deploy for data centers that can be leveraged into the EV charging world when necessary. And of course, there are some patents that Tesla wants to co-locate what they call their megapod. And so they want to have AI compute centers next to where they have power. And that's an interesting thing. It's like move to the, like Sam Kinison, we don't live in the desert, move to the food. So they put the AI compute next to where the power is. And so that's an interesting philosophy.
And we saw, I mean, it was confirmed in the Financial Times over the weekend that Tesla bought an energy company out of Jacksonville. We know that Tesla has the energy business that's growing with the megapacks, and they've got the semi, which I'll use the term is ramping up. From a Class 8 perspective, is Tesla the big driver of this, since they have the SpaceX data centers, they have the battery infrastructure, they have the charging infrastructure, and they have the truck in limited quantities? I want to, for the audience, limited quantities today. Is that the big driver today for this adoption?
Well, luckily in this case, it wasn't the Apple thing of the me, but the we. So Tesla knew that in order to support this many trucks in internationally, globally, nationally, has to use the same plug. You can't have things that are good here and not good there. So back in 2017, they were one of the leaders that pulled people together and pulled people and say, hey, let's work as a group to have this one standard. So when you say, are they a leader? Yes, they are. Are they the biggest financial force? Well, they have the deepest pockets. Are they going to own the market? Absolutely not, right? They're going to own a lot of the market. And, as we were talking before this, there's going to be international competitors who are going to say, we have things that look like yours, but have a different label on it. So Windrose just kind of melted, but they were definitely an example of somebody who was really close and looked a lot like the Tesla product without infringing or allegedly not infringing. But the point was the Me Too part is definitely not, much like laptops and other stuff. It's not going to, you're not going to own 100% of the market. You might own a lot of it, but not 100%. But that vertically integrated part that they have, the mega packs and Sunrun and, SSDs and data centers and stuff like that, that's going to be a big boost compared to everyone else who's doing things with their partners.
I'm super curious, and let's just say at scale, when megawatts deployed, what type of heat does the megawatt charger give off?
That's the good part about the conversion efficiency. So usually when you have big power, you want to keep your losses down so your cooling is down, and of course, just your net efficiency. So most of the big systems are running around 98%. And so if you just say 2%, then that's 20 kilowatt of heat, which again is very manageable when you have a big systems, big fans. And the same with the cables. Cables are generally short. We talked about the size of the contacts and then the area on the back of this with the cooling system and then having the cables short. So there can be up to 10 kilowatt of losses on the cable when you're pushing, 2,000-3,000 amps. But that's pushed out of a radiator. So it's not where you're standing, it's someplace remote. Just like your car, it doesn't push the engine heat into the cabin, it pushes out the back or the sides of the car.
I'm curious on that perspective. Are there environments where either because it's too cold, it's too hot, it's historically too rainy, flooding issues, where it is not safe to deploy megawatt charging today?
Not really. Everything is sealed. So I'll just kind of hold up some of the Scalability stuff. But you can see there's a locking motor on the top that makes sure that it's safe, that it's latched. You can see lots of O-rings and different sealing things between the bulkhead. This is the inlet to the thing. It's got temperature sensors, and so it always knows exactly what the limit is. And so that's really what happens on the too hot part. It will derate when it gets above its limit, and that's the key. And then the same thing goes with each of the pockets are sealed and they have drains. So just the quality of the connector says anywhere, anytime with isolation monitor and things like that. So there's pretty much no environment that is either too cold or too hot.
So I know you answered that, but now I'm curious. So let's just say you're megawatt charging in Death Valley in the middle of August. It's over 110 degrees. Does the charging slow down, or does it continue at the same speed?
The vehicles have their cooling system and the charger has its cooling system. And so as long as the cooling system is adequately sized for that location, it will still maintain, 1500 amps or whatever it's sized for.
Wow. And so how, from an engineering perspective, how is that possible? Is that all the interconnects, all the cooling? How is that possible?
Just big radiators. So everything there are liquid. I don't have anyway, I have them. They're just not here at the table because they're too big to pick up. But basically you can imagine the copper cross section, and then there's liquid tubes that are next to it that force coolant down the center of it. And so much like, cyborgs, there's just lots of tubes and wires and blue liquids going back and forth. But yeah, so and that's just thermodynamics 101. You need a big radiator and a big fan, or you need a compressor to move the heat from A to B. But that's just a matter of balance of system. We didn't talk about controls and interfaces, but the smarts from each of the sides also needs to measure those temperature sensors, and of course in some cases needs to be multilingual, where it would have both a CCS inlet on a truck and an MCS inlet. And so this controller is meant to speak three different languages, much like, some people are multilingual. And then we didn't really talk about adapters and reducers, but the point is that if you have infrastructure that is waiting for one thing, the other thing has to exist. And so there are adapters that go between the 8mm pins and the 10mm pins that are analogous to the NACS CCS. There are prototypes of MCS to CCS. And so those are also in that temperature limitations to say that if you have a CCS charger, it will not produce as much power as an MCS vehicle could take. So it's the smaller hose into a bigger hose. Bigger hose, smaller hose, you got a problem. Right? You're going to be rate limited. But the other way, going from a smaller to a bigger, that's why I use the word reducer. It's basically like a 3/4 inch hose to a 3/8 inch hose. It works, it just runs slower. Right, but it'll get you there, and that's where I think this interoperability and compatibility, and that's what I work on, is mechanical interoperability of measuring that things fit, measure the force, measure the change in impedance. So again, data. So Argonne National Lab, that's what we do. We don't make decisions, we make data, and the data is used to make decisions and, of course, to validate standards.
Is that data that you develop in Argonne with your colleagues, is that shared with industry? Do they come together with you either in a standards format, in a research format, to really, if you want to say, push the technology and see what's possible? Is that your role of pushing it to extremes?
Yeah, it is the validation stuff. So the papers, as you know, publish or perish. That's what I do. And so at ITech this year, I published a paper about mechanical interoperability and the overlap of solid state transformers and eVTOL and mining applications. So that's where we publish. And then of course in the weekly meetings is where we share and put it into the SAE folders. And that's why people often join. Just to be fair, people don't join the committee to help write. They join the committee to get access to see what's going on and to see how to do their homework. It's almost like, looking at sample problems in homework to say, how are we going to implement it? And that is the win-win on, if you can describe it enough to implement it, you've done a good enough job writing the standard.
Are there facilities with either at Argonne or you work with third parties where, let's say company A or company Acme will bring their product and you will push it to the limits to see if it's possible, does it meet that standard?
This is where I hand wave a lot, and I say there used to be. Something happened January of last year. I don't know what it is, but somehow all those facilities were closed. And I've had to recycle and scrap a lot of stuff. But They do exist. They're just not accessible anymore for something that happened last year. But we do have testables. And so we have events where people bring, much like a potluck, you bring chargers, you bring vehicles, you bring controllers, and you test them against each other. Those are sponsored by Charin in, East Coast, West Coast, and Central in Ypsilanti there is Charge Yard in the Sacramento area. There is American Center for Mobility in Ypsilanti. And so these facilities have a fee that they charge per hour to get access to things. So when you say, what do they do? It's kind of like renting a roller rink or whatever it is you get to do, or a racetrack, right? You get to do what you want for this many dollars per this many hours, right? And anyway, that's how it's done.
Is that basically like an adult version of the homebrew computer club where everybody bring all their parts together and you build stuff?
It is the round robin pass to the left, right? So you take, and that's what we used to have the what are called Plugfests, where you take your connector, and that's in fact why I have, just to kind of hold up a bunch of different things. So we got the stuff from TE, from Scalability, from others. Everybody sent me theirs, and they said pass to the left. I take the Scalability plug and I plug it into the TE one, and we just go round robin. That's really what these tests are about. So is you circulate. It's almost like the speed dating. You test in this one, and then every half hour you switch to the next stall and you test with the next vehicle.
I think that's fun, and that raises a question: as megawatt charging scales, how do you, your colleagues, and your friends in the homebrew clubs ensure interoperability?
That's it. So we had controller, like the controllers I just showed you. Those events are being hosted in Europe because it's easy to bring a controller there. The full size truck stuff is also happening in Europe because, again, those companies have not, for whatever happened in 2025, I don't know what it is, have not curtailed all their manufacturing development. But here, everybody else has pretty much hit the pause button, and therefore we have no testing events. We are ready at Argonne Lab. I'm like I said, I had big fixtures all set up, and for some reason, someone told me to throw a blanket over it until 2028.
When you're looking at the future and you're seeing what's coming down the pipe, what is the future of megawatt charging? And I'm curious, and if you can't answer this for reasons, feel free to say it, is that, do you see certain regions of the world that will adopt this before others, and why? And basically, what is the future of megawatt charging?
Not regions, but test cases or the use cases. So we talked about the mining stuff is 100% going this way. So there is no other, right? There is the automated stuff of J3105, which basically is really huge pin. I mean, like size of fire hose, right? So those exist already for 15 years. People are going to keep using that. They will use multiple sets of MCS, so they'll have not one, but like 3 of those on a robot arm. So that's absolutely happening. So Cat, Cummins, Komatsu, everybody's headed that way, and there are coalitions of people working together. The same with the Marine. The Marine will have a port and a starboard side drive system, and so you have a just like on a satellite tanks on a truck. You're going to plug in, and you're going to come in, and there's going to be one for the left side of the vessel, one for the right side of the vessel, and they'll run independently. Those are absolutely happening now. So lots in Norway, some in the U.S., and tugboats, things like that. So there's a whole bunch of vessels that greatly benefit on being electrified. That's a natural. So there are, I think, a dozen connector, inlet, and cord manufacturers. There are at least 30 EVSE manufacturers, and then, of course, of the vessels and the other systems, there are plenty. So just the takeaway message from this one is, if you want it, you can go buy it. And again, having fleets, like I said, Wadi V has 9 locations with MCS stations. They have 30 that are on the books. Tesla said by 2027 they will have 65 locations set on their roadmap. So everyone's set to go. And again, it's going to be a when, not an if.
It's clear megawatt charging is coming. And as we look to wrap up this insightful conversation, what would you like our listeners and viewers to take away with them today?
Scalability. So that when you see 1 or 2, that's okay. But then moving up to the other thing. The other thing is on this charge handle, and I'll just point out the one unique feature on this one is a small cable. You say, why is the cable so small on this one? And it's because you don't have to have a 3,000 amp pin that pushes 300 amps. You can set this up for 300 amp cables, and so you can the fast slow thing to say, everyone thinks they want Formula One pit stops. But you say, what if I work as a normal garage mechanic? So the whole idea of, how about if I wait 3 hours to charge my vehicle? How much less expensive and less complicated can it be when I charge at 300 kilowatt versus at 3 megawatt? And it's like, well, why do I always need 3 megawatts? Everyone thinks they want it until they see the bill. It's like, oh man, even the demand charge is going to be huge. So scaling MCS for aircraft, for other things, you can start at 300, the Tesla selling a 125 kilowatt system for $40,000, right? And so that base system is what you would have as your base. The thing that you need to charge overnight, that's ready to go. If you go to a full 1.2 megawatt charging station, right, it's X amount more money, but it'll get you out. So the whole idea, like with bandwidth on your phone, you got, the old 3G stuff is like, man, it works. It wasn't so great. But then 5G, 6G is like, wow, that's super fast. But I don't need 5G everywhere. I'll take whatever I can get to get the job done. That's one of the takeaway messages, that it scales. It scales both on speed and it scales on size. And then, of course, with multiple inlets on vehicles, you don't say, well, 4.5 megawatts is not enough. You say, yeah, but you can actually put multiple 4.5 megawatt in. It's like, oh, well, then they'll probably get it done.
I'll summarize this way. Megawatt charging is ready to scale. Today is tomorrow. Tomorrow is today. The future is megawatt charging.
That's a good title for a show. You should patent that.
I like that. Thank you so much for coming on SAE Tomorrow Today.
SAE International makes no representations as to the accuracy of the information presented in this podcast. The information and opinions are for general information only. SAE International does not endorse, approve, recommend, or certify any information, product, process, service, or organization presented or mentioned in this podcast.